12 days ago, Moonshot published Kimi K3. 2.8 trillion parameters, open weights, 1.5 terabytes sitting on a public download page for anyone. 4 days ago, somebody had it generating tokens on a MacBook. The video that put this run in front of 30,000 people quotes a speed 14.6 seconds per token. That number is already wrong. The project reports 3.76 seconds today, and it moved that far in a single day. So this is not a video about whether you can run Kimi K3 at home. You can. It is about which number decides that, because it is not the one everyone argues about, and the right one works on every model that follows. Start with the file. Kimi K3 is a mixture of experts model from Moonshot AI. 2.8 trillion parameters in total, but only 104 billion active on any given token. 93 layers, native vision, a 1 million token context window. The weights went up on Hugging Face on July 27th as 96 separate shards. On disk, that is about 1.5 terabytes. In the usual 16-bit format, the same model would be 5.6. The format is MXFP4 for bit block floating point, applied selectively. Expert weights go to 4 bits. Activations stay at 8, and the routers and attention projections stay higher, because that is where a rounding error becomes a wrong answer instead of a slightly worse one. And the part that matters most, Moonshot did not quantize this model after training it. They trained it that way, with quantization-aware training running through fine-tuning. The model learned to live at 4 bits. One note first, the license is not MIT. Moonshot wrote their own, and commercial inference above $20 million of revenue in any 12 months triggers a separate arrangement. Read it before you build a company on it. Now the number everyone quoted. Within days, Unsloth shipped a quantization ladder on top of the release. That is what turns a data center artifact into something a determined person can attempt at home, and it is where the famous figure comes from. The smallest build is 594 gigabytes. 2-bit is 861. 8-bit lands back at 1.5 terabytes, exactly the size of the original file. You pay for every step down. The 1-bit build agrees with the full model on 78.9% of next token picks. 2-bit gets that to 90.4. The smallest file is also the one that argues with itself the most. And Unsloth's guidance is that your combined memory should roughly match the file. For the smallest build, that is 610 gigabytes of RAM and VRM before it will load. That is the 610 everybody repeats, and it is a real number. It describes one specific approach: hold every expert in memory at once. VLLM says serving it properly needs at least an 8-way B300 node, and notes the model can barely fit inside a single one. Here is the number that actually decides it. Memory is not the constraint. Bandwidth is. The question is not how much you can hold, it is how many bytes have to move to produce one token. For a mixture of experts model, that number is far larger than the marketing suggests. Here is the trap. People hear 16 of 896 experts and picture 16 files. It is 16 per layer. The config is explicit. The first layer is dense, and the other 92 each route their own 16, chosen independently. The expert pool holds 82,432 of them, about 1.45 terabytes. 1,472 of those is roughly 25.8 gigabytes per token. This is why sparsity does not save you at home. Firing 16 of 896 experts is a 98% cut in the arithmetic your chip has to do. It is close to zero cut in the bytes that have to physically move, because the 16 change at every layer and at every token. In a data center, those bytes cross high bandwidth memory at 3.35 terabytes a second. 25.8 gigabytes takes 8 milliseconds. On a laptop, those same experts live on an SSD that reads at 5 to 7 gigabytes a second. That is the entire story. So here is the rule, and it outlives this model. Take the total size of the routed experts, multiply by the fraction fired per token, and divide by the bandwidth of the slowest link that data has to cross. That gives you seconds per token before you download anything. Every mixture of experts released from here answers to that same division. Which brings us to the laptop. The project is called DeltaFin, MIT licensed, published by a developer as Gavamedia, and it went from 274 stars to 525 in about a day. It runs full Kimi K3 on a 2021 MacBook with 64 gigabytes of RAM. It splits the model in half. The dense spine, the attention layers and shared experts and embeddings stays resident in memory. That is about 114 gigabytes, or roughly half that once compressed to 8-bit, which is what makes a 64 gigabyte machine viable at all. Everything else it refuses to load. For each token, the router names its 16 experts per layer, and DeltaFin reads exactly those. One range request per expert, 17 megabytes at a time, into a disk cache that grows as you use it. You need the disk. 1.7 terabytes for the full install and 5 to 10 hours to pull it down, or 215 gigabytes if you stream the rest on demand. That second option costs about 3 minutes per token. The limitations are stated plainly. Greedy decoding only. Temperature and top P ignored. One request at a time. The documentation tells you to set client timeouts to hours rather than seconds. And it never trades away quality. All 16 experts are used, and the model stays the sole authority on every token. So it works here. Now point it at everything else. Run the division. 25.8 gigabytes over an SSD that reads at 5 to 7 gigabytes a second. That is somewhere between 3.5 and 5 seconds for one token. Measured, it is 3.76 seconds per token. The arithmetic got you there without touching the machine. It comes in slightly under the naive bound because the engine uses lossless speculation and that growing disk cache, so not every token pays full price. It is running at its storage limit, not past it. Point that same division at the rest of the open weight field, and the ranking is not the one you would guess. Kimi K3 fires 104 billion parameters per token. DeepSeek V4 Pro, 49 billion. GLM 5.2, 40. Minimax M3, 23. Qwen 3 Coder Next, 3. 3 billion is the number that changes everything. At 4 bits, the entire Qwen build is 46 gigabytes, which fits inside the same 64 gigabyte laptop with room to spare. Nothing streams off the disk. It never pays the tax at all. So the open weight field splits cleanly in two. The trillion parameter models stream experts off a disk and answer in seconds per token. The small active models sit entirely in memory and answer in tens of tokens per second. Same rule, opposite side of it. One last warning, back on Kimi K3, steady decode went the same way. Roughly 20 minutes a token, to 14.6 to 3.76. Every write-up I can find still quotes the old figure, and this video will date just as fast. The engineering is moving quicker than anyone can report it. So what should you actually run? The honest answer starts with a different technique. Quantization keeps all 896 experts at lower precision. Pruning deletes most of them. Reap, from Cerebrus, scores every expert by how much it actually contributes and keeps the ones that matter. The aggressive build keeps 242 experts of 896 and lands at 451 gigabytes. Its own model card says it targets Apple Silicon machines with 512 gigabytes of memory. That prune is not free either, and the card is refreshingly honest about it. It calls the degradation noticeable. The model drifts into list-shaped or source file-shaped continuations instead of answering, and at heavier ratios it falls into outright repetition loops. Code completion survived better than general writing. And now the part nobody has connected. That build targets a 512 gigabyte Mac Studio. Apple deleted that machine. That configuration vanished in early March with no announcement, and the 256 gigabyte upgrade went up $400. The consumer ceiling is 256 gigabytes now, so the recommended local build targets hardware that stopped being orderable 4 months before the model shipped. And the cause is the sharpest part. A global memory shortage, because manufacturers shifted production to high-bandwidth memory for AI data center accelerators. The data center build-out ate the supply local AI needed. So, the weights are genuinely free and genuinely enormous. 610 gigabytes of RAM was never the wall, because you can stream experts off a disk instead. The wall is 25.8 gigabytes of traffic for every token, divided by whatever your slowest link can carry. That is the calculation to keep, and it will still be the right one for the next model. Deltafin's own README is right about what it built, an existence proof, not a chat setup. 3.76 seconds a token is not a verdict on the project. It is a reading off the storage bus, and that bus is what stands between a downloaded file and a usable assistant. Sources for every number are in the description. Follow InferenceWire for what the AI headlines actually mean.